In Chapter 18, we discussed probability models. Probability models are very similar to distributions in that they tell us the possible ways in which something can occur and how likely each occurrence is. These are the concepts that we will discuss in Chapter 18. Probability models, probability rules, probability models for sampling, and the sampling distribution. To classify chance behavior, we need to know two things. First, the possible outcomes for some random phenomenon, and also how likely each of these outcomes are to occur. This leads us to the definition of a probability model. A probability model for a random phenomenon describes all the possible outcomes and says how to assign probabilities to any collection of outcomes. We sometimes call a collection of outcomes an event. For example, here is a probability model for the marital status of American women. We can see that marital status can take one of four values, either married, never married, widowed, or divorced, and also how likely each of these outcomes are. For instance, if a woman is selected at random, the probability that she has never been married is 0.455, according to this probability model. Before we come up with our own probability models, we need to discuss some basic rules of probability. Some of these will be reviewed. First, any probability is a number between 0 and 1. If an event has probability 0, it never occurs, and if it has probability 1, then it always occurs. Next, in any probability model, the sum of the probabilities for each outcome must be 1. As a probability model must list all the possible outcomes. Third, the probability an event does not occur is equal to 1 minus the probability that it does occur. This is called the property of complements. As an example, what is the probability of rolling something other than a 1 when a 6-sided die is rolled? Here the probability is 1 minus 1 over 6 or 5/6. Where 1 over 6 is equal to the probability of rolling a 1. Last, if two events have no outcomes in common, the probability that either occurs is the sum of their individual probabilities. For example, what is the probability of rolling a 1 or a 2 with a 6-sided die? Here, both 1 and 2 occur with probability 1 over 6. So the probability that either are observed is 1 over 6 plus 1 over 6, or 1/3. Let's use the probability model for marital status to investigate some of these properties. First, notice that each probability is between 0 and 1, and when we add each of the four probabilities, we get 1. Also, let's use the property of complements to compute the probability that a randomly selected woman is not married. If the event not married does not occur, then the woman has to be married. So, the probability she is not married is 1 minus the probability that she is married. So we get 1 minus 0.494, or 0.506. As another example, what would the probability model for the outcome of rolling two 6-sided die look like? Here there are 36 possibilities, and because the dice are fair, each is equally likely. So each of the 36 outcomes has a probability of 1 in 36 of occurring. Let's use this probability model to answer a question. What is the probability that the sum of the dice is 5? Here we will use the last property of probability that we discussed. First, we will list all the outcomes in this event and then add their probabilities to arrive at our answer. So how many different ways can this event occur? If we refer to our list of the 36 possible outcomes, we see that there are 4 ways in which this event can occur. Either 1-4, 2-3, 3-2, or 4-1. Each of these outcomes has a probability of 1 in 36 of occurring. So the probability that we roll a 5 is 4 out of 36, or 1 in 9. Let's relate this theory to something we talked about during part 1 of the course. Recall when we discussed sampling, the value of a statistic changes from sample to sample due to sampling variation, and thus is a random phenomenon. To understand what values the statistic could take and how often these values are taken is prescribed by the statistic's distribution. The sampling distribution of a statistic tells us what values the statistic takes in repeated samples from the same population and how often it takes those values. We think of a sampling distribution as assigning probabilities to the values the statistic can take. Because there are usually many possible values, sampling distributions are often described by a density curve, such as a normal curve, rather than listing the outcomes and their probabilities in a table. For example, suppose we take 1,000 simple random samples of size 2,527 from a population to estimate some proportion p. Here our statistic is p hat, and the distribution of values from each of the samples is shown in the histogram. We see from the shape of the histogram that p hat has an approximate normal distribution, and the imposed normal curve shows the idealized pattern from the results of a very large number of samples. Let's do an example. An opinion poll asks a simple random sample of 501 teens, generally speaking, do you approve or disapprove of legal gambling? Suppose that in fact exactly 50% of all teens would say yes if asked. The poll statisticians tell us that the sample proportion who say yes will vary in repeated samples according to a normal distribution with mean 0.5 and standard deviation 0.022. So what is the probability the opinion poll will get a sample in which 52% or more say yes? First, we must compute the standard score of 52%. Because the mean is 0.5 and the standard deviation is 0.022, we see that it is equal to 0.9. Next, referring to Table B, we see that a standard score of 0.9 is in the 81.59 percentile. Finally, using the property of complements, we see that there is an 18.41% chance of observing an opinion poll in which 52% or more say yes. Let's do one last example. The sample proportion who say yes will vary in repeated samples according to a normal distribution with mean 0.5 and standard deviation about 0.022. According to the 68, 95, 99.7 rule, what is the probability that fewer than 45.6% say yes? 45.6% is exactly 2 standard deviations below the mean. We know that 95% of samples will be between 45.6% and 54.4%. Because of this, 5% will either be below 45.6% or above 54.4%. Finally, by the symmetry of the normal curve, exactly 2.5% should be below 45.6%.